the Wiki Lunch is a series of lunchtime talk hosted by UKFin network. UKFin is a network funded by the Engineering and Physical Science Research Council. And our key goal or objective is to enable industry and the researchers to collaborate more. And this network is particularly focused on that collaboration issues or the joint efforts between two sides for financial services. We have launched our research agenda, which you can find out on the UKFin website. And we have different spotlights that address the new problems coming up relating to technology and solutions for services, for financial services. We have run the first spotlight on financial inclusion, and now we are moving to this current spotlight on game-changing technology. We ran 3 lunchtime talks. The first one was on AI, and today we're going to talk about quantum computing. And on the 5th of March, we're going to run another lunchtime discussion on blockchain technology. Without further ado, I'd like to introduce our panelists. And we have a very exciting panel today. We have Professor Bill Buchanan. I don't know whether you've known him. I've known him. I talked to colleagues about him, and my colleagues basically said to me, I've been following this guy, the real expert on cryptography on YouTube. And I understand that, you know, if you are studying this area, he's one of the best teachers you can follow. So please check him out. We also have Ross Grassi with us, and Ross is leading a quantum software lab at University of Edinburgh. While we are, you know, looking for speakers, you know, he attracts our attention simply because he cares about technology and the real impact and applications of the technology in quantum, in financial services. So you can't find a better speaker than him. And the final panelist is Marcel. Sorry, Marcel, your surname, if I pronounce incorrectly.
I know it's hard.
Apologize.
Don't worry.
And he basically representing the new minds and the new brains, you know, for the upcoming technology generation. And he has background in both physics and computer science or data science, and he knows a lot of applications in this area. So now, I think I don't need to even say more. You can see that we've got expert panel, and I'd like to just dive into the topics today. So first of all, I'm going to go around and to start the debate with the panel, and then we're going to open up the floor for the audience to ask questions. And at the same time, if you have questions, please do use the chat function and put your questions in. We will have my colleagues here to monitor your question, and we'll put that to the panel. So first of all, great panelists, could you quickly tell us what is quantum computing in simple words and in technical words? Bill, do you want to go first? What is quantum computing?
I'm not a physicist. I'm an applied cryptographer. So my understanding of quantum computers doesn't quite go down into the qubit level, but I do understand that we can represent our ones and our zeros that we would in a normal computing world as qubits. And the exciting thing is that we can break away from Moore's law. So Moore's law defines that every 18 months or so, we double the computing capabilities and memory and processing and so on. And as far as I can tell, we're down to around 4 nanometers for a transistor. I remember a long time ago when I did microelectronics, my transistors were 10 microns. So in the space of a decade or so, we've now moved down so that the transistors are almost so small that we can't go any smaller. So quantum computing will allow us to be able to break away from Moore's law and to start to run our processing much faster than we did. And basically what we're doing is that rather than representing the states of 1 and a 0 in a transistor, we're now looking at qubit states and using optical or liked methods to be able to do the processing. The days of the AND and the OR gate and the NOR gate will also go, and we'll start to look at quantum circuits and quantum logic gates. So my work is really looking at how, for one, quantum computers will actually break our existing cryptography methods, all of our public key encryption methods, elliptic curve, and RSA will be completely broken by quantum computers. And that's a real worry, because the whole of digital trust, in fact, on this network connection now, we are using a public key method to make sure that we can secure the communication. So that's a worry for us, that quantum computers will actually cause that disruption. But where it becomes really interesting is that when we can apply machine learning methods and use quantum circuits to simulate the methods that we have just now. So that's my quick overview.
I think you pretty much cover the give us an overview of the points we're going to go through later on. But let's get to Ross. Ross, what is quantum computing for you, especially from the application side in financial services?
I think Bill did a great job of covering a lot of the technology. I think I kind of had a much shorter answer, which is just to say that I normally view quantum computing just as a new area of emerging technology in the same way that AI is or blockchain is. It's just a new piece of emerging tech. We believe it could have a profound impact in financial services, but we don't know where it's going to be used, how it's going to be used, or when we should start using it. So that's a lot of open research problems where it's definitely going to need quantum computing researchers, but it will absolutely require financial researchers to come in with the domain expertise so we can figure out how on earth we're actually going to use this new piece of emerging tech as well. So I think at the moment I'll kind of stop there, but that's what quantum computing is for me.
Thanks. So Marcel, from both Ross and Bill have said, sounds like quantum computing is a lot faster. It will be needed to, solve a lot of the application issues, especially while we are going, fastly moving to the data world. Are there any other benefits that people, or like ordinary people or organizations, the business, really should take notice of this emerging technology?
There is plenty actually, and I'll build on what Bill said to explain why. Because I think of quantum computing as some sort of expansion of what we can do with our computing machines. Bill mentioned that we're at 4 nanometers of manufacturing our semiconductors. The problem that we face is that we can't go much further because atoms are roughly this size. So it's just impossible. And I think the biggest application of quantum computing is that it allows us to play by different rules. It's not just zeros and ones anymore. We've got many more tricks that we can use, be it for the security of the systems. And for example, my favorite property of quantum systems is that they are not as easily copyable as the classical systems. On the other hand, we've got, because of this new paradigm of computing, we've got possibility for new algorithms, new security tools. We can just compute things not only faster, but in a different way. And for that purpose, I would think of quantum computing as composing music, because quantum mechanics tells us that all those building blocks of quantum computers are like waves. We can compose them, and out of that we get a completely different picture. And obviously applications of that span many different areas. And to answer your question directly, I think we'll benefit most from that in terms of simulating new quantum systems. So let's say drugs, complex systems in general, so financial dependencies between banks that can be mapped onto some architectures that quantum computers admit very easily.
Sounds good. But where are we in terms of, the quantum computing from theory to like applications, real life? Where does the UK stand? Where, you
I
know,
would say that
what
our
do
minds
people?
are way ahead of our bodies when it comes to it, because we've got plenty of ideas how to build algorithms. As Bill may expand, we know that there are algorithms that threaten our current encryption methods, but we can't implement them yet, and that's where we struggle. And although there have been some demonstrations of quantum supremacy or quantum advantage, as people say this, well, name this situation where quantum computers do something that classical computers can't do, we have to face that with caution. For example, the recent announcement by Google about their quantum chip is perfectly legit. They do something that classical computers wouldn't be able to do. The problem is that this is a benchmark problem. No one really cares if we know the solution to it. So I would say we are getting there, but we're still a few years away.
Okay, sounds good. But you know, I think the speed of seeing this technology emerging is already kind of quite astonishing. I'm just wondering, you know, from all your experiences, do you have some like real life examples, especially
Sure.
like say financial services, like banks, insurance companies, are
Sure.
kind of on
So
those adoptions?
yes, so that's another aspect of the problem, that we can't say, oh, it's going to happen in a few years. We already have to be wary of threats that quantum computers can pose. There is the harvest now, decrypt later problem that some other people may expand on. But in terms of the applications that financial services use today, we can name randomness generations. There are already platforms that allow you to use this commercially available randomness from quantum systems. We've got some approaches to machine learning, especially when it comes to synthetic data creation. That's what people are interested in. Some commercial banks like JP Morgan have shown that there is a scope for quantum communication that is encrypted differently than classical communication. There have been some demonstrations of communication protected by quantum key distribution at the distance of 50 kilometers. And from the physical point of view, that's very interesting, because if we assume perfect conditions, this should be unbreakable. Unless you're very, very lucky, you just guess the key, you shouldn't be able to intercept that. So these three areas, I think, are already in use today.
Sounds good. And Bill, I saw you sharing some, yes, even a paper that possibly tell us a lot about applications.
Yeah. So when you think about it, what we need to do is we're simulating with quantum circuits just now. That's just simulation. So that's just using a classical computer, and we're simulating with our gates and with qubits and so on. That's great for pretending that we're using a quantum computer. But what we need to do is to build real use cases on quantum computers. So the paper that I've published, I think, is quite unique in that it uses both methods. It uses a simulator and it also uses a real quantum machine. Unfortunately, we're only up to about 100 qubits. So things like creating a big machine learning model is going to be difficult, and cracking encryption is a long way off, even though those Chinese researchers have said that RSA has been broken. So in the work that we did, we analyzed domain botnet domain generation. Do you know, sometimes you get a domain name and then you'll get a strange extension to the domain name, which is random, which is obviously is something like barclays.com, and there'll be a random name after it. This is how botnets can actually create fake websites by randomly creating these additions. So what we did was that we took a data set with all these domain names, these randomly generated domain names, and we tried to understand the entropy within each of these URLs, and to make some judgment as to whether this was generated by a bot or by a machine. we could only use 100 data samples on a real quantum computer. We use 3 real quantum computers on AWS and Microsoft, but then we simulated 5,000 data samples in our simulator overall. And we found that the data was actually better than our traditional machine learning models. So we think the real challenge is to start to scale the simulations into our real quantum computers. But the expense of that has to be seen. Like on just now on AWS, it's free for a certain amount, but obviously once the free time is gone, then you'll have to pay for that. So we don't quite know what the business model is, but I can assure you it's likely to be very expensive to run on a real quantum computer. So I think academia needs to understand that and to start to provide not free resources, but just like we have high performance computing, could we have a quantum infrastructure for the UK and for Europe? And I think Europe plays a big part in this. I think we've got to build bridges from the UK into the EU much more because we're part of the Horizon project. So what's going on in the EU, and can we build resources that allows us to be able to test our things and not just use simulators?
Yeah, Ross, let me get to you. Thanks, Bill. And you actually mentioned the quantum computers, the real quantum computers. That's actually something I'm going to ask Ross. Ross, do we have real quantum computers in the world? And yeah, where we are at?
Yes, there are real quantum computers, but the error rates are humongous, and you're not going to see a practical use of them yet. So I think, as Bill was saying there, the simulations at the moment are actually marginally more useful than running on quantum devices. If you've got these kind of application projects, normally the way that they look will be that you'll have on pen and paper, you think it should perform like this, your new quantum algorithm for option pricing or fraud detection or whatever it is that you're interested in. You will then run a simulation, which might perform slightly worse just because of implementation issues. And then you'll run it on a quantum computer, and that line will be significantly worse than even your classical simulation. It's still useful to have the theory, the classical simulation, and the actual QPU run to see how far away those lines are. But in terms of the hardware development and pushing to the scales at which you will find practical use of a quantum computer, I think we're not particularly close at the moment. It depends who you talk to. If they're really ambitious, they maybe say a couple of years. If they're very pessimistic, they say never. So it's somewhere between that range, is that you're going to see some practical use of a quantum computer for a financial application.
Great. I mean, you mentioned the HSBC, and we're going to come back to that in a minute. But can I just actually plug in a question? I mean, even as a researcher myself, engaging with technology, it's quite confusing to understand all these terminology like quantum, AI, machine learning. Can the panelists give the audience a little bit kind of explanation or ideas? What's the difference? And what's the similarity? And where the applications, in real world?
Yes, I think common misconception at the moment with quantum stuff is if people say, oh, it's a big data problem that's going to really scale terribly, and then I know they might bucket quantum with AI there. That's not the case. Getting a lot of data into the size of quantum computer that you have at the moment is not a good idea. It's not good. So if you've got a big data problem, stick with AI. I think quantum computing is very interesting in the way that you have to formulate the problem, even on pen and paper, will be completely different from how you have to formulate it if you're thinking about classical techniques. So that is kind of where it becomes very interesting, is if that different way of thinking then becomes useful for your application, then you maybe want to go down a quantum route, and then you can start to worry about qubits and modalities and all this kind of stuff. But if you ask yourself up front what kind of problem it is, it might well be that you actually don't want to dig into the technicalities of quantum computing. You just want to stick to AI or other classical techniques. Sorry, Bill, you've got your hand up.
Yeah, in fact, I was going to ask you, Bill, you were mentioning the growth of the quantum chips, right? And it broke the old law. Now it's kind of growing in like a double exponential speed. But we see the investment in AI seem to, really outshines the investment or even awareness of quantum. Do you want to chip in there?
I draw a Venn diagram. I hate to bring it back to Venn diagrams. I draw cryptography or cybersecurity. I draw AI and I draw quantum together. And you can overlap each of these areas. If you just stay in one domain, then you've lost it. Okay, if you look at the example of the Chinese bot that was created, they didn't even have a secure connection to a back-end service. I mean, who tested that? So to me, our researchers need to be looking at cybersecurity and privacy. I bring in privacy. When I talk about cybersecurity, I'm probably talking more about citizen privacy, making sure that citizen data isn't harvested by these bots. And then in a world of AI agents, you've really got to worry that there's going to be these AI agents going around with all our personal data that could be mugged virtually and steal all our data. So to me, the Venn diagram is most interesting in the part where everything actually meets together. If you think you're going to do AI on its own, then you've lost it, because AI needs ethics, it needs an audit trail. I need to get my data out of the AI model. If Google has scraped my website for intellectual property and didn't have my permission, then GDPR says that they must take that data out. So I think we're in a world that's really harvesting data like anything. All the intellectual property in the world, all the books in the world are being harvested for AI, and we need to be thinking much more about privacy and security. So if you bring the areas together, then we need to actually think about the processing infrastructure that we need. And if we're going to be harvesting massive amounts of data, we can't do it with our existing methods. It's eating up the planet for electricity just now. Microsoft have got a massive data center, the biggest data center ever being created in the US just now. And I think they're building nuclear power plants to actually provide this there. So we really need to be thinking about the next generation of processing. If you take an example in cryptography, Grover's algorithm says that I can search through 2 to the power of 128 different keys in almost in an instance. That is a quantum leap. You try to do 2 to the power of 128 on a computer, and I'll see you in millenniums, if not billions and billions of years. That's not possible just now. So Google want this. Of course Google want it, because Google have trillions of index terms, and they want to identify data and things like that. They can't cope, and AI can't cope with the models that we have. But with a quantum computer, we can have 2 to the power of 128 searches for something in an instance. Well, not in an instance, but in a short time. So to me, it completely moves out of the box of silicon, which is slow. We can't scale it anymore. So we actually need to be thinking of better methods. And our electronics will move to optical methods, and we won't be held back by gigahertz. My clock and my machine is 4 gigahertz. That's tiny. We need bandwidth that goes up to tera or pica, things like that. So it will move, and 6G is coming along, and 6G doesn't do silicon very well. It does millimeter, and then onto micro, and then onto nanometer. So it's a new world. And if the UK doesn't match the US and China, and the EU is struggling too, then we're going to lose our industry completely.
Yeah, thank you so much. Marcel, I possibly need to come to you. We start to talk about challenges. It's clearly quantum computing is very exciting, but at the same time, it's very challenging. So what's the, again, this is from the audience, what's the biggest engineering challenges stopping us from building I mean, not the real quantum computer, but actually usable quantum computers
Sure.
that industry, financial services would actually use or feel confident and safely to use?
Mhm. Let's focus on the quantum computing platforms for the starters. And also, let's refer back to your question, what's the biggest difference between classical and quantum? The biggest difference for now is that we don't know what's the best platform to do quantum computation yet. We know that for classical, that we just need plenty of semiconductors. Whereas in quantum, every single company has got its preference, and they've invested a lot to prove or disprove that it actually works. And all those platforms have got their own problems. Ross has mentioned the error rate. So, in plain words, the quality of what we call the quantum transistor. But I think the biggest one is scalability. We to have some practical implementation of the algorithms that break the encryption, we need roughly 10,000 logical qubits. We are at the depending on the provider, we're at a moment in history when we've got at most 100. So because we don't know how to network these computers, because we don't know what architecture will work the best, we are quite far away from implementing those most revolutionary algorithms. And I think if you were to ask me, it's not just enough to produce plenty of qubits, because it turns out that algorithms have got the preferences for hardware, which is not that obvious when we think of classical computation. And for a very simple example is that for some algorithms, you need to have some connection between all the qubits. Or you have to make up for that producing more and more qubits, which we can't do. So I would say this is the biggest challenge right now in quantum computation. In some other areas, we've got some other challenges. I've got experience in cryptography, so I can talk about the technologies like quantum key distribution, where again, we can't do it on long distances without some reinforcement. And for example, that's the reason NSA in America deemed that technology not preferable, because they don't believe that it's going to be repairable soon, to make up for those challenges in delivering this technology, even though the promises are great and the proofs of concepts have been shown numerous times. So yeah, one word, scalability.
Okay, thanks. I think, because you guys are all the experts in this, you have great belief in quantum computing. But for general audience, or users, when there's a new change, especially like kind of revolutionary changes, people have a lot of worries, and then they're thinking how safe it is, what's the threat? Like, for example, we all know the Y2K, when it came, but are we actually, going to the quantum era expecting something like Y2Q? That's kind of level.
Well, so actually,
yeah,
let me answer to that with an example from cryptography. Roughly 2 years ago, at the conferences of quantum cryptographers, people were saying that there is going to be the Q day and the NISQ day. And let me explain you what it means. The Q day is the equivalent of year to quantum sort of thing. So when we actually have got hardware that will make this change happen. But what people were actually much more interested in was the NIST day. So when the standards, when the law changes, when the regulations require you to care about quantum, and that already happened roughly half a year ago. So I would say that it's sort of similar with quantum computation. We can lure ourselves into thinking that, oh, it's so far away. But in fact, it may happen that our infrastructure will require us to already care about that, even though quantum computers are not yet in place. And yeah, out of that, you can make plenty of money actually, because if you can make company comply with a regulation, they are happy and they can already buy your products. So yeah, that's my answer to that.
That's great. I think the business would all love your idea of making money and ahead of the curve. And Bill, do you want to add more onto that?
Yeah, so this is my topic area. This is my passion. And there are two things in this. There are Peter Shor's algorithm, which will factorize prime numbers. So the way that RSA works is that I take two large prime numbers, I multiply them together, and it's a hard problem for you to find the two prime numbers in there. If you can find those two prime numbers, then you break it. The other method is called elliptic curve cryptography, and it's based on discrete logarithms. G, a base to the power of x, mod of a prime number. It is really difficult to find x, even though you know G and P in there. At the present time, the silicon that we have and the processors that we have, that's a really difficult problem to have. But Shor showed that it's possible to crack both of these methods using waves, and it's end of story, which means that our public key encryption method, so public key is used for key exchange. So the key we've used to secure this channel has been negotiated between all of us, and we have an encryption key to secure it. That stops people from stealing our data and doing a man in the middle and so on. But the key thing, or the most important thing, is the digital signature. How can I tell that I'm dealing with Zoom and I'm not dealing with a fake Zoom? That works because we use a digital signature. The website signs with its private key and sends me a signature, and I prove with the public key of the server. If it wasn't for that, we'd go back to HTTP days. I don't know if you can remember HTTP days, but they were terrible. You could not prove any website at all. I could fake a website quite easily, and you would never tell. So for one, we break key exchange. That's all of communications. And for two, we break every bit of trust. When you log into your web service, you're typically using SSH. You're using your private key to do that. So the connection to the cloud. So every single thing will break, and I can assure you it's much worse than Y2K, which is just a little software bug that we could fix. A bank has billions of keys at any time. It is creating key pairs all the time. If it loses its private key for its website, it's in big trouble in that people can fake their website, they can hack anything that they want. So Y2Q is going to be much worse. And luckily, NIST have said that we will deprecate all of the existing public key methods by 2030, and we will remove them by 2035. So if you're a bank, 10 years isn't a long time, and I can assure you 5 years is not a long. You need to be FIPS 140 compliant, or you shouldn't be working as a bank. So we see lots of banks in Edinburgh who are now looking at replacing all their existing public key with a hybrid method. A hybrid method means that we run the existing method, such as RSA, and we run the new one, dilithium, or Kyber for key exchange, at the same time. And eventually what we do is we drop the existing method, and we'll end up with a post-quantum. So cryptography has always healed itself. A vulnerability has been found, and we increase the key strength. One last thing is that 128-bit AES and hashing methods are not secure anymore because of Grosvenor's algorithm. So NIST have recommended, and all over the world, agencies have recommended that we uplift a 128-bit encryption and hashing to 256-bit. And again, that causes complete disruption. So this is real this time. The last time was fake.
Yes. Okay, Maciej, just a very quick one, and I want to actually plugging
Sure.
or spraying a little bit more.
Just a bit of context to what Bill said. The estimates say that just in the US, transferring from classic current cryptography to post-quantum cryptography is going to cost 7.1 billion over the next 5 years. So this is a huge challenge, and banks really care about that.
Yeah, actually, I'm so glad, both Bill and you mentioned this, because as I mentioned, we had the first financial inclusion spot, and we talk a lot about, how you see financial services from a consumer perspective. And FCA and a lot of regulatory bodies are, really on the task. Because the trust is a huge issue. The future generation of customers have to fully trust and then entrust their data to you. So the privacy or safety issue will be a massive, massive thing. So Ross, I know you are working and advocating this area. Could you just share a little bit, from the regulation and compliance perspective, where we're at? Yeah, opportunities and challenges, etc.
I think for regulators, it's still quite early days. I think having seen everything that's happened with AI, they're very keen to not be caught out quite the same way with quantum technologies. So I know, for example, the FCA have worked with the World Economics Forum and have released some thinking on post-quantum cryptography that was recently kind of advocated by the G7 as well, which is fantastic that the UK are leading in that kind of thinking. Literally 2 weeks ago, I've also started working with the FCA, which is going to be on a piece of work which asks exactly this question of, okay, say it goes very, very well. Say that researchers in the UK end up coming up with the best quantum algorithm to do options pricing or fraud detection or whatever it is that people are wanting to do, credit scoring. Does that actually impact the existing regulatory framework? Yes or no? And it could be that it doesn't. It's just that an increased computational power or efficiency or speed or whatever doesn't actually change the regulation. Or it could be that it changes it very profoundly depending on the use case. So it's still very early days in the thinking, but if, the FCA do seem to be world leading in this. And yes, if there's anybody in the audience who is interested in that discussion, please do reach out, because like I said, we started 2 weeks ago. We want to release a white paper by the end of June, which will be bringing together industry thinking, academic thinking, and government thinking on how quantum is going to impact financial regulation. So if you would like to have that discussion, please do reach out.
I would even say that the statistics say that our audience should be reaching out to you, because
Absolutely.
roughly 84%, as the Quantum Safe Financial Forum says, 84% of banks feel that 86% feel that they will implement some post-quantum solutions, but only 84%. As much as 84% think that they won't be ready. They are not sure if it's going to be enough. So there is a clear misalignment between the understanding what quantum is in that sector and what is required.
Absolutely. So I know the NIST standards had been mentioned before as well. The FCA in the UK and FINRA, their equivalent in the US, have been talking very closely with NIST about the standards that are there and how they should be signaling to banks about their preparedness and what they should be doing to make that transition. So all of these bodies are talking together, but yeah, incredibly early days. As I've said in my intro, we still don't actually know even where quantum computing will be applied in 10 years' time. So trying to figure out what the regulation should be where you don't know where it's going to be used other than in cryptography, that's quite a difficult thing to try and comment on. Sorry, Bill, I also got your hand up again.
Yeah, Bill, go ahead.
Oh yeah, so there is advantages in this. So The downside is that the encryption keys become bigger. So just now, 32 bytes of keys sizes for elliptic curve is going to go up to 800 for Kyber. So there will be an overhead in this, and our digital signatures, which are quite small just now, will actually increase. So every bank needs to understand the overhead, the latency, the performance that's created. But I think the opportunity is that we can start to build new encryption methods within quantum computers, and that's a big area just now. So with this, we take AES. I can't believe they can do this, but they can actually create S boxes. S boxes are like a scrambling box within AES. AES is probably what we're using just now to secure this communication. Researchers have actually created a quantum circuit to do that. And when you think the opportunity that we could actually start to encrypt data within a quantum computer would be amazing. Researchers at Edinburgh have also created a one-shot signature that doesn't reveal the private key. It is not possible in silicon to do this, and don't ask me about the physics of it. But I can create a digital signature with a one-shot in a quantum computer, and you cannot find the private key that was used to sign that. So with signing, what happens? I have a key pair, a public key and a private key. I sign with my private key the data, and then you will prove with the public key. Researchers at Edinburgh and other universities have actually created the possibility that I can create that signature, and you will not find the private key which replaced that. So in areas like blockchain, we can really see our world of zero-knowledge proofs, of privacy-aware computing coming alive in a quantum machine, because it's almost physically disconnected from our real world, our silicon world, and we're now into a quantum world where you can preserve. You can't stick a probe into a quantum machine and actually find out. Well, you probably could, I'm sure, but I think there are new quantum things that we could start to look at, and I think that's on the near horizon, and will really push. Quantum key distribution has had a difficult birth. Some people love it; it's like Marmite. Some people hate it with a vengeance, and really, the use case for quantum key distribution hasn't quite happened. The big problem is that I need light fibers all the way from one to the next. I've seen research papers that talk about quantum key distribution in 5G networks. If you can start to do that, that opens up a whole world of opportunity, that it's now radio waves that you can do it. And in our 5G, 6G networks, you can actually start to look at proper entropy key generation and salt generation using the quantum methods, but in a radio space.
Yeah, that sounds great. Actually, while the panel was going on, I was actually thinking of a few real financial services related examples. We all know the industry revolution has gone to Industry 5.0, and so is the banks. So are the banks. We're moving from the banking 4.0 to 5.0, which really advocates human personalized solution driven kind of AI type of solutions. That links to what you were saying, Bill. People over time, have to give a lot more data, and then there will be massive, trust and the data privacy issue. So I guess security and all these issues would be a challenge, but at the same time, it presents a lot of opportunities. But also, on the other hand, I want to talk a little bit more on the financial services focused area, especially with emerging technology. Some people call them disruptive technologies, and because they disrupt the current structure. The fraud detection seems to be a topic. I mean, we discussed that before in past decades, but that topic become very urgent problems to be tackled and talked about a lot. So can quantum computing really benefit those areas? Again, linking to what all the panelists are talking about on the privacy and the safety issues. Ross, I saw you already ready
Yes.
to. Yeah.
So yes, I've been working with HSBC for the last year and a bit on looking at quantum machine learning for fraud detection. And yeah, I think it's one of those really interesting use cases because especially since the pandemic and the cost of living crisis in the UK, the amount of fraudulent transactions going through has actually increased quite dramatically. And it's also a use case where even if the accuracy of your detection rates gets better by a fraction of a percent, you're going to save millions of pounds. So it's a very nice use case when you're still trying to figure out whether this technology will actually be useful or not, because even if you do get that very, very marginal improvement, that actually does have a very big societal impact. I think the impression that's coming out of that project is that, well, as we've been saying before, if you're wanting to run something on a quantum computer right now, possibly not. However, out the back of that project, we are running tensor network simulations of quantum machine learning techniques that are providing value over and above what was already implemented there. So, okay, the solution that's coming out isn't running on a quantum computer, but because we thought about it in a quantum way, we're coming up with a quantum-inspired solution that is providing value at the moment. So I think, and it depends on how you want to define value. I think that's a very valuable thing that's come out of this project, because thinking about it in a quantum way has led to a better solution. And then it starts to get you on that path towards maybe in 50 years' time, when we do have fully fault-tolerant humongous quantum computers, it will be kind of a derivative of what we've been doing today. So yeah, I think there is a path for quantum providing value for that particular use case.
So Bill, quite quick comment.
Yeah. I mean, really, we've got to get rid of our computers that we have just now. They're silly. We have 32 and 64-bit registers, and we're trying to do machine learning with polynomial values of 1,000 bits. A machine learning method uses the NTT mainly. It's a basic computation of a dot product of a vector. It is such a simple, but to do that on these silly machines that we've created is just stupid. So that's why GPUs have taken off, because GPUs can do that basic computation of the dot vector. I mean, what is a machine learning? It's a vector and a matrix times a matrix times a matrix, and so on. There's no specialness actually in the core computation that we do. So our machines are finished. I mean, really, they're gone. And we need to look at machines that do lattice methods. So lattices are like polynomial values that we have. So in cryptography, the new methods that we have for public key encryption are lattice-based and are proven secure. So the computational base that we have with a quantum computer doesn't have these limits of memory, silly memory, and registers, AX registers and BX and all of that. So they break away. So we should be able to do much better computation than we do just now on a quantum computer. So anything that can run in a machine learning model just now, if we scale that into a quantum world, it should run much, much faster. And I think that's the true essence of where quantum computer will go, is to actually apply it into machine learning. From my side, I see the vision as homomorphic encryption is the holy grail. Homomorphic encryption means that data is encrypted in every single state. It's never decrypted. My heart rate can come off my watch and it's encrypted and Apple can use it, but they can't actually tell what it is. And you can use that data in a machine learning model. So it's possible to create an SVM model, train it with 80% of the data and test it with 20. You then move that into a homomorphic encryption engine where you can encrypt the data coming in. And from the fraud point of view, why don't banks share information? Because they're not allowed to, and it's sensitive information. If we could move to a homomorphic encryption world, that data can be encrypted. Okay, it could be poisoned, that's a bad thing. And then everyone in the community can share the data together in a machine learning model.
Yeah, safely. That's the main thing, with current data sharing. Yes, so Ross, you only allowed a few seconds. I'm joking. Quick comment.
No, that we're going into the last 10 minutes and we do want to open up for questions as well. It was just, yeah, to very quickly say when Bill was saying to get rid of all classical computers, I think for quite a while to come, it will still be a world in which quantum computers act as accelerators in the same way that GPUs or FPGAs or something do. Just because something can run on a quantum computer doesn't mean it necessarily should run on a quantum computer, just for ease of use. And maybe it's energy efficiency, maybe it's just cost. These things will not be cheap for the foreseeable future. So yeah, it will definitely be both. It's not quite that everybody's got to chuck out their classical computer anytime soon. So just to kind of flag that.
Yeah, but you know what? Actually, because you guys laid the foundation so well, I didn't feel so daunting hearing Bill said, our computers are finished. Okay, now please, if you are in the audience, and send your questions in, and I'm going to raise to the panel with some questions already asked by the audience. So we heard, while we're talking about quantum, we heard another word coming up a lot is universities, research, etc. So apparently, with all other emerging technologies, the talent pool is a big issue and is a big focus. If we want to do this, we have to plan ahead. What's your views on training the next generation or retraining current people? Any advice or any priority you think we should?
Ideally, sorry.
No, go.
Ideally, we should start in the kindergarten, just expand the knowledge capital of children. I know I sound like the new math project from the 60s in the US, but if we think about that, there is this mystique around quantum. We say, oh, if it hasn't profoundly surprised you, you haven't understood that. But do we teach evolution this way? Do we teach biology this way? No, at some point of evolution, some facts are taken to be obvious, and maybe the new principle of computation should be one of them. So that's one thing. Another thing is that there is a huge underrepresentation of certain groups in quantum. Just 1 in 54 quantum job applicants is a woman, and this is terrifying. We can't let that happen. And finally, I'd say that obviously we need something now. So the best solution is to do. Uh, uh, it's nothing groundbreaking, but we have to embrace this idea of buffet scientists. They go into the technological buffet, they take whatever they need, and maybe that's their only interaction with quantum. And yeah, perhaps a PhD shouldn't be needed to work in this area. Perhaps we should expose people just to a fragment of all that knowledge and let them change their institution.
Yeah, sorry, Bill. I know you're going to add something, but I'm going to ask you a different questions that audience asked. So if somebody wanted to study, say, undergraduate to get into quantum area, what would be your advice? Do they study a math degree, computer science degree? What should they do?
And really, my advice, I do a lot of open days. My always advice is typically you talk to the parents rather than the actual candidates. My advice to parents is to generalize for undergraduate and specialize for postgraduate. If you specialize too quickly on, say, quantum computers at undergraduate level, you're going to paint yourself into a corner. So get into computer science, get into maths and computer science or something. The doors will not be closed for you. Get into software development and things like that. Get some practical skills from your undergraduate. And then you decide the job that you want to do. And the jobs in 4 or 5 years' time are not the jobs now. That's the other thing. When I get asked, is there a job in cybersecurity for me? I can say there is one now, but in 3 years, there might actually not even be a discipline called cybersecurity. All our jobs are changing completely, and all of us have got to be adaptable. My advice is to get into software development, move up your skills one level. So if you're at this level with your skills and you're wide and thin for your topic areas, then you need to get deeper. AI will replace that long and thin. So I'd say, and I got into cryptography and I went deep. And the deeper I went, the more I loved the subject and the more I understood about it because I had a gap in my knowledge. So pick things and find out what's missing that the university professors didn't teach you and trace back. And even though you didn't do maths and you've lost maths for 5 years, get back into it. I can assure you ChatGPT does not do maths, does not understand abstract principles. Don't tell OpenAI I said that, but it's a superficial knowledge. So to me, get deep, get developed in your skills and really try to broaden out overall. And I go back to the gender thing. I totally agree. We have a training course that teaches cryptography, blockchain, and AI and cyber, and we have 55% female attendees. These are engineers who want to learn deep technology. Luckily, we got a partner from Turkey, and there are places in the world that don't have this gender balance, where there are young, eager female engineers and scientists who want to get into this area. So we shouldn't be just looking into the UK or our own cities. We should be building bridges and knocking down walls. That's what I say.
Yeah, sorry. I think we've only got 4 minutes left. So I do have a question from the audience to ask about advances of quantum that potentially can bring to the medical and healthcare. Possibly we won't have time, sorry, that to answer that question specifically, but I hope you already see the benefits, you know, from the general discussion about quantum's advantage and even challenges, etc. We're just going to go around the final round, and Ross, I saw you hands up. Maybe while you do your final round, you can say a couple words about this question. But I would like to, towards the end, ask all the panelists, you know, very, very quickly to tell the audience 2 takeaways. One, what's the biggest challenge? And second, what's the biggest opportunity of quantum in finance, financial services, and other, you know, application areas? Okay, so Ross, you go first.
Yeah, just very quickly on the healthcare and life sciences, I think it's a bit further away, but things like drug discovery, simulation of, I don't know how drugs are ingested into various bits of the body, that's kind of useful, and also synthetic data as well. Getting lab data is very difficult, so we've been working with bioinformatics here on that. Can discuss more if you'd like. But yeah, in terms of the biggest challenges, I think still scaling and finding those use cases. We need both of those things to happen. And in terms of exciting opportunities, I think especially in financial services, I do think the kind of data privacy stuff of your quantum machine learning, there's also these concepts of like blind quantum computing as well, which are very interesting for protecting data, especially as we use more and more AI. So those are my kind of takeaways.
Okay, Maciej. Challenges?
Scalability, that's for the challenge. For the opportunity, as I might have mentioned, quantum lets us do as much as physically possible. So obviously we want to be able to compute more, and this general thought should lead us.
And Bill, please do wrap up for us. Challenges and opportunities.
Challenges. Well, would you want a list? Skills gap, massive. The bridge between industry problems and academia is increasing, and it's quite worrying that academics work on one thing and industry has all these problems and the two don't meet together. So we need to address that. And post-quantum cryptography is going to decimate our world. I hate to say it. The world of finance needs to wake up very quickly and address that. And I echo the other 2 panelists. Machine learning and quantum computing, if it's done properly, will bring forth a new world of computing, and it can be a privacy-aware one. Thanks.
Great. Thank you so much to all our panelists and amazing discussion. And thank you for your participation from the audience. And just towards the end, when we wrap up, could I just ask the panelists, if the audience have more questions, would you be happy for them to reach out? Yes, okay, great. So yeah, that's definitely okay if you write down the panelist's name, and then they like myself is from Imperial College, and then Bill is from Edinburgh Napier University, and Ross is in University of Edinburgh. Brilliant, thank you so much. But if you have further questions, please do get in touch with UKFin, and then look up our funding streams, especially as Bill said, we do fund projects that close the industry and academia gap. So thank you very much for your participation at this lunch hour.